Today's video is focused on in Class 7, which is the second day of notes for standard number 2, all about angles. In our introduction today, we have been tasked with finding the measurement of several missing angles. And so if we think back to yesterday's notes with in Class 6, I'm noticing a straight line, actually two straight lines, that are intersecting in these diagrams. So if we think about our linear pair theorem, yesterday we learned that these two angles should add up to be a total of 180 degrees. So if 65 degrees is the measure of angle AEB, we should be able to find the adjacent angle that forms that straight line, the measure of angle BEC, by doing a quick subtraction from 180 degrees. So this angle here would be 115 degrees. A similar thing will happen if we focus on the other straight line in the picture. So again, the measure of angle BEA is 65 degrees, and then this adjacent angle would have a measure from A to E to D, also of 115 degrees, to make that total 180. And if we rotate back to the first line that we used, we can use this 115 degree angle we just found, which would be adjacent to this last angle here, angle CED. So the measure of angle CED would be 180 minus 115, which takes us back to 65 degrees. A similar situation is going to happen here in example B. So if we look at this straight line, we would be able to add these two angles together to equal 180 degrees. 180 minus 95 leaves 85 degrees left over. And we rotate to another line. The same situation happens with these two adjacent angles. So subtracting from 180 would give us 95. And if we do that one more time, either with these two angles or these two angles, subtracting 95 from 180 would give us 85 degrees. So all of that work is based on what we've learned previously is called linear pair theorem. We just use that idea over and over and over again. But what ends up happening is it actually brings up another idea that we can use to solve problems as well. So if we look at these two angles across from each other, they ended up to be matching, both 65 degrees. The same thing is true on these two angles, both 115 degrees. The same thing happened here, both 95 degrees. And then lastly here, they were both 85 degrees. That relationship is what we're calling a vertical angle relationship. So if we're looking at that diagram, we need to first define what vertical angles are. We are going to describe those as two angles across from each other when two lines intersect. So we're describing this situation of two intersecting lines, and we're talking about these angles that are across from each other, or these angles that are across from each other. So kind of like the definition of a linear pair, that just tells us how vertical angles look. But if we work on that idea a little bit farther with these examples up top, we've also noticed that there's something very specifically true about vertical angles. We're going to call that the vertical angles theorem. So if you want to actually highlight or circle or put a star, that vertical angles theorem is going to be another reason we can use when we're solving problems. If two angles are vertical angles, then they are, I'm going to use a new symbol for us today, congruent is that symbol. Congruent is a word that tells us that things are the same size and the same shape. So in terms of our algebra problems, we can think about it in the same way we would think about the word equal. But the vertical angles theorem is something we're going to use for a pretty long time, and eventually we're going to transition away from things being just equal to being more specifically congruent. So I want you to kind of have that symbol ahead of time. It's just an equal sign with a squiggle on top. It means things are the same size and the same shape. So in terms of solving problems, we can use that idea anytime we spot something in a picture that looks like the definition of vertical angles. So we have two intersecting lines right there. They intersect at point E, and we're looking at the angles that are across from each other. And so we can mark these in a way that matches to show that we're using the vertical angles theorem to solve the problem by saying the angle on the left, so that would be the measure of angle REG, has to match or is equal to the angle on the right, which would be the measure of angle AET. They must be the same size. So if we switch into algebra mode, we're going to have 13x minus 15 on one side and 10x plus 6 on the other. And then you can do your algebra to solve that equation for what x is going to equal. You should end up with x equal to 7 at the end of that solving. Do a quick geometry double check. They wanted us to solve for x, so if I could show this all on the screen at the same time, I would write x equals 7 in that answer blank at the bottom of your page. Alright, so that is now the fourth reason that we've come across in Standard 2 for solving problems dealing with angles. We have 2 more to go through, and then we'll be done with all 6, and we'll be ready to start reviewing and practicing to get ready for our assessment. Alright, that's a little bit clearer. Hopefully that helps. Our last 2 are both definitions. So if you want to highlight or star or circle and mark that these 2 are our last 2 reasons that we're going to be able to use, we will define and then we will do an example of each so that you can see how they work. Alright, first things first, the definition of complementary angles. So complementary angles are going to be 2 angles that add to a very specific amount. Some of you might already know what complementary is because sometimes they show up in a middle school math class, but 90 degrees is the amount, and they are allowed to be adjacent, which means they're allowed to look like a right angle in a picture that's been split up into 2 adjacent angles, but they don't have to be next to each other. In fact, we might not even have a picture given to us at all. We might just have information that says complementary. That's the only way we'll actually use the definition of complementary angles as a reason. If we see that word printed, then we know we're going to use the definition of that word as our reason for our work. So what our equation does is it takes the 2 angles that are complementary and it focuses on how those 2 angle measures, so the measure of angle DEF and the measure of angle LMN, would need to equal 90 degrees when added together. And you can put the degree symbol in your equation or not, that's up to you. Substituting in what they've given us, 43 was the measure of angle DEF. We're going to add to that the measure of angle LMN, 6x plus 5, and even though we can't see it in a picture, they told us the word complementary, so we know that it's going to add up to be 90 degrees. Once you do your solving, hopefully you're combining like terms. 48 plus 6x equals 90. Subtract that 48 over, 6x equals 42. So x is going to be 7. If we do a quick check, x was all we were looking for, so x equals 7 is acceptable to put into our answer blank. Our last type of problem is the definition of supplementary angles. So our final reason, the 6th one. Supplementary is going to be angles that still add up to a specific amount, but not 90 degrees like complementary. Instead, supplementary angles add up to be 180. You might be thinking, well, wait a minute, that sounds a whole lot like linear pairs. And you're right, it is very similar to a linear pair, except a linear pair must be adjacent, and supplementary angles are not necessarily adjacent. So instead of seeing a picture of a linear pair like we did up in the top in the introduction, we will see the word printed out. If we see that word printed out, just like with the word complementary, we know that what we're going to use in our problem for our reason is the definition of supplementary angles. So it's not based on what we see in a picture, like it is for vertical angles theorem or linear pair theorem. It's based on that vocabulary word and understanding that vocabulary word. Very similar general equation, though, to both complementary and linear pair theorem. We're going to take the measure of our two angles that are called supplementary. They'll be added together, just like they were with complementary, but they're equal to 180 degrees this time instead of 90. And that general equation doesn't look any different if it's a linear pair theorem problem. It's just a different reason because you're noticing it from a picture versus noticing it from a vocabulary word like we are in this one. So if we substitute our values in, the measure of angle DEF is 3x plus 2. We're going to add to that the measure of angle LMN, which is x minus 6, and together they're going to make 180 degrees since they're complementary. A little bit more to do this time with like terms, since we have x's that can be combined and constants. I'm going to add 4 to both sides, and then when we divide, x is going to turn out to be 46 for this problem.